What is going on, guys? Welcome back to another from scratch tutorial. We're going to implement a Gaussian Naive Bayes classifier in Python from scratch, meaning using only core Python and NumPy, and we're also going to discuss the theory and the mathematics behind it. So let us get right into it. Alright, so we're going to talk about Gaussian Naive Bayes in this video today, and we're going to implement the classifier from scratch in Python, which means we're not going to use anything except for core Python and NumPy. We're not going to rely on scikit-learn or any other machine learning package. We're just going to use NumPy to work with arrays efficiently, to do some basic linear algebra without having to implement broadcasting and so on ourselves. But besides that, we're going to implement the pure math in Python and, as I said, NumPy. So we're going to talk, as I said, about Gaussian Naive Bayes, and this is what I always like to do with these from scratch tutorials. I like to start with a section where we go through the theory, the mathematics, so we understand actually what is happening behind the scenes, and then once we understand that, we can put it into code, which I would recommend as an exercise here. So if you watch the first part here, the mathematics, the theory, take that knowledge, maybe also go to Wikipedia, read up on the math again, and then try to put it into Python code. And if you fail, or also if you succeed, then watch the second part to see how I did it here. But I think this is a very good exercise for intermediate programmers. Now, with the name here, Gaussian Naive Bayes, we have three terms that are very important. We have Gaussian, which points to a normal distribution, a Gaussian distribution, which doesn't look quite like that, but you get what I'm talking about here. We have a Gaussian distribution behind the scenes, a normal distribution. We have naive, a naive assumption, and then we have Bayes because of the Bayes theorem. So for this algorithm to understand it, you need to have some basic understanding of probability theory and statistics. You need to know what Bayes theorem is, you need to know what probabilities are and how they're written, what the individual symbols mean. You need to know what it means for features or variables to be independent, and you need to understand what a normal distribution is and what a standard deviation and a variance and a mean is. If you don't know that, I recommend reading up on the basics, but we're going to require these things as a basis here for this Gaussian Naive Bayes algorithm and classifier. So the Bayes theorem is actually quite simple. We have a probability. Let's say the probability here is that we have some class that we try to predict. We want to know what is y, what is the class that I'm trying to, what is the class of the data that I provide you with here. And the probability that this class is equal to some class k, given our input data x, is equal, according to Bayes' theorem, to the following thing. It's equal to the probability that y is k regardless of the data. So this is a prior probability. Just in general, how likely is it for y to be equal to k without knowing anything about the data yet? That times the probability of seeing the data x if we know that y is equal to k. So that is like the reverse of that. And that whole thing divided now by the probability to see the data x in general. Now, this is ordinary Bayes theorem, nothing too fancy here. This is not naive Bayes, this is just a Bayes theorem. But based on that now, we can proceed to build this Gaussian Naive Bayes algorithm here. Now, one thing that we're going to ignore for the most part is this lower thing here, the px. Why? Because what we're interested in here is comparing probabilities. Gaussian Naive Bayes works with computing two probabilities and then just siding with the greater one. So if you have, for example, let's visualize this in a simple way. If I have here some data, and with Gaussian Naive Bayes, we have continuous data. So there's also multinomial naive Bayes and different distributions that you can use, but this one allows us to use continuous data. And with this data, what we can do now is we can do a classification. For example, is my data yes or no? This could be something like, will the person pass the exam? Yes or no? Or is this data pointing to a dog or a cat? Maybe in the case of an image. Or in our case, what we're going to do is we're going to use a breast cancer data set. So we're going to classify tumors to be malignant or benign. And how we do that is we compute a probability for this class, we compute a probability for this class, and then we compare, and the greater one wins and is our prediction. That is our basic idea here. And since we are comparing these probabilities, this lower part doesn't really matter because the data is always going to be the same, and we're always going to divide by the same data, or by the same probability in this case. So we can just, for the most part, ignore this. Now, in addition to all of this, in addition to ignoring that, we also make a naive assumption. Now, I need one more color here. The naive assumption is that this thing here, in reality, is going to be quite complicated. Because if I know the class y is equal to k, then the probabilities of the individual features are not independent. A very, very simple example of this would be if I know the height of a person, it's not independent from the weight. So the probability that a person has a certain weight does change when I know that the person has a certain height. So just multiplying the probabilities together only works if they're completely independent features. But height and weight are arguably related. So if someone is very tall, then probably they're also going to have a little bit higher weight. And there's also, of course, some other stuff. Some other basic example would be, to go to the extreme now, someone like sugar. This is not independent from whether they like cake or not. Now, maybe it's not the same, but there is some relationship there. But we do make a naive assumption here for naive Bayes, and this naive assumption is that we can just say the probability of x occurring when y is equal to k, when we know the class, we just say that's the same as the product j starting at 1 going up to d, which is the number of features. So that is the number of features. The product of the probability of a specific feature occurring under y equals k. So we just take the product of all the probabilities, which only works if we have independent features. So we're multiplying them together. That's a naive assumption that this is true. And with this naive assumption now, we can take the formula and rewrite it as follows. We can say the probability of y being equal to k given the data, which is of course what we're comparing, right? We're getting this here for one k and then for the other k, and then we're just looking at which one is larger. But that thing we just say is proportional now. This is proportionality here. That this thing here is proportional to p, y is equal to k. So that is just a prior probability here, y being equal to k. And that thing times this product here, this j1 up until d product, like this, j1 up until d, of the probability that xj, the individual feature, is what it is when y equals k. Of course, again, in reality, this doesn't make a lot of sense because the probability changes if I know that a person is very tall. The probability for the weight feature is not unaffected by this. And now what we also do, since this is a Gaussian naive Bayes, is we take this probability here for the individual features and we model these according to a Gaussian distribution, or you could also say a normal distribution. And there is a fancy n that you need to draw for this, something like this. I'm not sure if that's correct, but it's just the probability that xj occurs as the feature value given the mean of this particular feature for the class. So k for the class, j for the feature, and the variance for that feature, kj. And then here's squared, because this is the standard deviation. Standard deviation squared is variance. So we are saying that the probability of a feature occurring given that the class is k is the same as taking this feature or calculating the probability of this feature value for the mean and variance in a normal distribution, giving the mean and variance of the respective class. So we base all of this on existing data. So think about it that way. We have our data set, and what we do is we just say, okay, the prior probability is how often does the class occur out of all the examples. So if I have 100 examples and 30 of them are class K, I have 30% probability that this is going to be the class without data. And for this normal distribution here, I just use the mean from the data, the mean of feature J within all samples of, or all instances, I should say, probably, of class K. And the same here for the variance, right? That is the idea. Now, to put this now into mathematical terms even further, this is the same as 1 over square root of 2 pi variance for kj times e to the power of negative xj minus the mean of jk squared divided by, come on, I need the line tool here, divided by 2 times the variance kj. That is the exact same thing, just written as a formula. This is what we have here on the left, just written in exact mathematical terms. So here now I only need to plug in the variance again, the mean, the actual value that was observed, and there you go, we have the probability. So we can put this into Python code. For this here, for the prior probability, it's very, very simple. All we need to do here is we need to say we take the number of instances with class K divided by the number of instances. And maybe to finally define this correctly, let me take the yellow color for this. What is the mean? So maybe we can get an arrow here for the mean. What is the mean? The mean for kj is just the same thing as 1 over nk, since we're getting the mean. So we need to divide by the number of instances times from I, where the class is equal to k. So all the instances where the class is equal to k, xij. Just sum up all the values, divide them by the number of features of this class. And for the variance here, we just say kj squared. It's just the same thing. 1 over nk times that. I is again where the class is equal to k. And here now we just do the standard deviation. So minus the mean of kj squared for the variance. So we basically have all the ingredients, and this already makes sense. We have, of course, the features. We have, of course, the prior probability because we have data. This is all based on the data. We can also calculate the mean based on the data and the variance based on the data. So actually we're done here. However, we're not quite done because we also need to consider something called underflow. Multiplying very small probabilities together leads to an underflow, which means the values get so small that computationally speaking in computers, they don't make a lot of sense and the changes don't work. There's numerical instability here, which of course mathematically is equivalent. So in terms of pure math, it doesn't change anything, but in terms of computation on our computer, it does change something. So we need to work around this. We don't want to multiply small probabilities together because they get super small and meaningless. So what we're going to do is we're going to apply the logarithm to turn multiplication to addition and thus resolve the problem. So we take this beautiful part here, this yellow part, or this white part, I should say, and we rewrite it with the logarithm. So we just take log of this. So we say log of py equals k given x. The logarithm of that is equal now to the following, or proportional, I should say, to the following, the logarithm of the prior probability, so y is equal to k, plus the sum. Now the product turns into a sum because we're working with logarithms. J equals 1 up until d, and of course we take the logarithm of the probability. So xj, sorry, I forgot a p, xj y equals k. There you go. That is now our new formula. And of course, we can now take that and turn it into actual numbers and values by using these formulas here. Well, I would say that the interesting part here is just this thing on the right. So let's just ignore this because this is just a logarithm of the probability. But maybe as a context here in general, what are we doing here? We're predicting the correct class. This is a classification algorithm, remember. So what we're trying to do is we're trying to argmax. We're trying to find something so that we maximize the following term here. So we try to find a k, the class k, to maximize the term here, to maximize this probability here, to maximize the log props. That is what we're doing here. just as a context. So this part here is very simple. We just have the logarithm of the prior probability. We can ignore that. The interesting thing here is the normal distribution part. So what we do is we have here the sum. So actually we're only interested even in that part. So in the small logarithm part, because that is the same as the logarithm of, so what is this probability? It is the normal distribution, right? So we have our fancy normal distribution with xj here as the value, with the mean for kj and the variance kj. That is what we're trying to calculate here. And what this means is it's the same as this huge term that we had before, this little thing here. So again, 1 divided by square root of 2 pi variance squared times e to the power of negative xj. So the value minus the mean squared, and then divided by 2 times the variance. And the interesting thing is we can now calculate this even further. First of all, this whole thing here can become a sum. So we can actually do it like this and turn this into a sum here. That is possible. This is just logarithms. And then we can treat them individually. So what do we have here? We have the logarithm of, and then we have 1 over. So that's the same thing as saying 2 pi variance kj, and then that thing to the power of negative 1 over 2. So that is the same thing as 1 over square root, right? And because we have a logarithm, what this means is we can extract this out as a factor. But let's do the right side first here. What do we have here? We're working with a logarithm base e, so this gets canceled. And we have basically just the term negative. So actually we can remove the plus here, minus, and then xj minus mean kj squared divided by 2 times the variance. So that would be kj here again. So what we have here is we have negative 1 over 2 times logarithm of 2 pi variance for kj minus, and then basically that's also 1 over 2, but we can just keep it like this. So xj minus mean kj squared divided by 2 times the variance. That is the final thing. This entire thing here plus the prior, that is what we're looking for. This is what we're trying to maximize by choosing the correct k. So what I'm going to do now, I hope you understand this. Maybe let's briefly recap just as a context here. What is our goal? We're trying to figure out what class is correct, the correct classification for the data. We get some data. In our case here for the breast cancer data set, it's going to be lengths and widths and depths or something like just continuous value describing the shape of a tumor, I think. And our goal is to figure out what the correct class K is to label this data as. And we base that on the data that we already have. So we look at the existing data. What we do with this existing data is we calculate the mean for each class. We calculate, and for each feature as well. So for each class and for each feature, we calculate the mean value and the variance. We also calculate the prior probability for each class. So how often does it occur in the data set in general? And then what we do is we use a normal distribution, the formula here for a normal distribution, to estimate all the probabilities. We multiply them together here with the prior probabilities, but due to numerical stability or instability concerns, we do everything here as a logarithmic probability. So we add them together, and that is the thing that we get as a result here. This plus the priors. And this is now what we're going to put into code. We're going to see it works with the actual data set. We're going to get a high accuracy rate. All right, so now let us get into the practical part. We're going to take the mathematics we just discussed and we're going to put them into code. For this, I'm going to go to my tutorial directory, and in here, I'm going to create a main.py file. Now, before that, what you want to do is you want to install NumPy onto your system. You also do want to install scikit-learn, but not because we're going to use it for actual machine learning stuff. We're just going to use it to get the data set so we can evaluate our model on the data set. And we're going to use it for basic stuff like train test splitting. So not for any machine learning stuff, but for the pre-processing and for the data set itself, and also for the evaluation. So what you want to do is you want to use pip or pip3 install, and you want to install numpy. You want to install scikit-learn. These are the two packages. In my case, what I'm going to do is I'm going to set up a UV project. So UV init, UV add, numpy, and scikit-learn, just because I don't use my system Python installation. It's just not considered a good practice on my operating system, which is of course Arch, by the way. And now what I'm going to do is I'm going to go into the main file and I'm going to start with the imports. We're going to just import numpy, snp, and the rest is going to be imported once we're done with the implementation. So I'm going to implement this as a class. I'm going to call this class Gaussian NB in the same way it's called in scikit-learn. And in this class now, we're not even going to define a constructor because we don't need to pass any arguments. Theoretically, you could pass a value for variance smoothing, like a very small value for numerical stability. For the sake of simplicity, I'm just not going to do that here, just to keep the code concise. I'm going to start right away with the fit method. So this is going to take self, x, and y. So x is the matrix with the data, y is the actual correct classification. And we're now going to train our model based on the data that is provided. So we're going to first turn the data into numpy arrays. So np.asArray x, whatever the data is. So np.asArray y as well. Then we want to know what is the set of classes. So what possible classes can I have? And for this, we're going to say self.classes underscore is going to be equal to np unique, so get the unique values from y. And then we want to know the dimensions, so how many classes do we have and how many features do we have, because based on that we're going to create our arrays with the means and variances. So I'm going to say here n classes, n features is going to be equal to length of self.classes and x shape index 1. What this means is x shape index 0 would be the number of instances, but we're interested in per instance how many features. So that's the second dimension, index 1. That gives us the number of features. Now we're going to prepare empty numpy arrays with, or for the priors, for the means, and for the variances. So self.means underscore are going to be equal to np.zeros. Now for each class and for each feature, we want to have means. So we're going to say n classes, n features. We're going to have the same thing also for the variances. And now for the priors, we don't need that dimension because for the priors, we only need to have one probability per class. So np zeros n classes. And now we iterate through all the classes. I'm going to say for index and class k. So for index and class k in enumerate self.classes. So we iterate over the classes and we also have an index. I'm going to create a matrix xk, which is all the data. So all the input data where the correct classification is k. So where y is equal to k. And now, very simple, I'm just going to say self.means is going to be at this position. So self means index is going to be equal to the mean using axis 0 of this particular set of data. And I'm going to do the same thing here for the variances underscore is going to be the var function. And for the priors, it's even simpler. We just need to say the number of instances that we have for this class compared to the total numbers. So xk dot shape, this time index 0, because we're talking about number of instances, not number of features, divided by x shape 0. xk is only the instances with the class k, and x is all the instances. Once we have this done, we just return the instance, so self. All right, and now comes the mathematics. This is now the only thing that we need to do based on our great sketch here. So we need to put this whole thing here into the formula, but basically we now need to take these log formulas here and put them into Python code. So I'm going to do this here. I'm going to say there is a function here called underscore log underscore Gaussian self given some data x And we're now going to apply the formulas. So let's maybe start with the right side here with this xj minus the mean squared divided by that. So what we have here basically is, let's call this num is equal to negative 0.5, which is 1 over 2. Here we have an imaginary 1, and here we have the 2. So 0.5 times, and then we have this thing. However, we need to do this now in the NumPy way. So we need to take x, but we need to say, give me the first dimension, so all the samples, give me none, so no classes here, or not considering the second dimension here, and then give me everything again for the features, and we take that, and we take that minus the means. So self means, actually I also need to put that in parentheses here, self means underscore squared. That is the top part. We now also need to divide by the variance. So we take all of this divided by self dot variances. That is that. Now let me center this. And the second part now is this on the left here. This again, 0.5, negative 0.5 times logarithm. For this, we're going to use NumPy. We don't need math. So I'm going to say here for the log prop, I'm going to say negative 0.5, or actually we should consider num already. So we have one part already. It doesn't matter if I take the right one minus the left one or the left one minus the right one, because they both have a negative sign in front. So I'm going to say num minus 0.5 times np log of 2 times np.pi. I hope this exists. I think so. Times self dot variances. And very important, we also need to specify axis is equal to 1. And since we have all these log probabilities, of course, in the beginning, the probabilities had to be multiplied. So we had a product, but here what we do is we just return a log prop dot sum axis equals 2. So let's get rid of the graph here. That is basically the math that we discussed, that we derived. This is the log Gaussian here. And the only thing left to do now is the prediction logic. So def predict is going to be using that. We're going to get some x as input. We're going to say x is going to be turned into an array if it isn't an array already. And then we're going to say log likelihood is equal to self.log Gaussian x. And then we say the log prior probability. We didn't have that yet. Remember, we just implemented this bottom part here. We didn't talk yet about the prior probability, which is nk over n. So the log prior probability is equal to np log self dot priors. We calculated that as well. And now we have these two, and of course we need to add them as well. So we need to say self or return self.classes. Now we can do that in one go. So we can choose the class where this probability is the highest by using argmax. I can just say np argmax the following. I want to maximize the log likelihood plus the log prior probability on axis 1. And that is basically the thing. Which class do I have to choose to maximize this sum here, this probability sum of the likelihoods, of the log likelihoods, and the prior probability? That is the whole logic. This is a Gaussian naive Bayes implementation. Definitely there's a mistake in there because I don't record anything without having one typo or more in my code. So I'm sure this is not going to work first try. But regardless, what we're going to do now is we're going to import from scikit-learn the data set and also some evaluation mechanisms just to see if this works. So I'm going to say from scikit-learn.datasets, we're going to import the load breast cancer function from sklearn dot was it model selection. We're going to import train test split, and then from scikit-learn metrics, we're going to import the accuracy score, I think, right? Yeah. All right, and then we can use this just like any other classifier. So we load the data, xy is equal to load breast cancer, and we're going to say return xy is equal to true to not get this as a data frame. And then we're going to do a train test split, x train, x test, y train, y test, is going to be equal to a train test split performed on X and Y with a test size of 0.2. I need to set up auto completion here in my new Vim. Been too lazy to do that. And then we're going to say here classifier is equal to Gaussian Naive Bayes, and we're going to fit that directly on X train and Y train. And then we make some predictions on the test data. The Y predictions are the CLF predict on X test. And then we compute the accuracy score, which is going to be, which one was the first one? I'm not sure. Was it first prediction, then test, or was it test and then prediction? Let's just do it like this. I'm not sure if this is the correct order, but it should not matter too much. Now I can just run this, in my case, by doing UV run. In your case, just by doing Python or Python 3 run, Python or Python 3 main py. In my case, UV run main py. And what I get here is a problem, of course, because we have priors, and I didn't include the underscore as it seems. And we also have no axis for the logarithm. Where did I do that? Oh yeah, obviously we don't need an axis here. Besides that, there you go. We get 93, 96% accuracy, 92% accuracy, 92, 89, 91. There you go. We implemented Gaussian Naive Bayes from scratch in Python. So that's it for today's video. If you want to see more of these from scratch tutorials, let me know in the comment section down below. Let me know which algorithms you're interested in the most. And also don't forget to hit the like button to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thanks much for watching. See you in the next video and bye.